Thanks a lot. Thanks everybody for trickling in after the lunch. I want to give you a little bit of an overview of many things that we have been doing, and towards the end, I think I will also give you a few examples of how the different pieces are coming together, and how I think that some of the some of the ideas that I've heard, I have been listening at least to the talks that were not totally incompatible with my time zone. And I think that some of the ideas about, creating workflows that combine different tools in a modular fashion is very much a consequence of, compatible at least with what we have been trying to do. So in terms of the field of application, I'm very much, at least for the moment, grounded on the modeling side and on the atomic scale modeling side. But of course, the idea of doing modeling at the atomic scale is usually to feed information to coarser-grained level of description. But yeah, for the moment, I'm going to focus in particular on the atomic scale side of the story. And of course, this is an industry that has been flourishing for at least 60 years, and hardware progress and theory progress have brought modeling a long way, but still the fundamental challenge that in order to get accurate results, you need to solve accurately the electronic structure problem and to sample accurately finite temperature thermodynamics and fluctuations is still a challenge. And this is really, as many others who have spoken before me, the core idea of what we're trying to do is really to make it possible to do this as accurately and much more cheaply using machine learning. Now, here I have to stress that this is not necessarily the the most mainstream direction in which machine learning is moving. I think for good reasons, there is a lot of effort in trying actually to get the end answer straight from the simplest description of the chemical system that you're working with. So this is what I call end-to-end prediction. And the kind of idea is that you start from something like just the composition of your material or of your molecule, and you predict what will happen when you put that molecule inside the human body, or what would happen when you make a device out of that material. So the sort of intellectual space in which we're moving is more the bottom-up idea. So the idea is that still we go through a sequence of steps that gives us the mechanistic insight on why a molecule behaves in a certain way, why a material performs in a certain way. And, I think that there is value in this. And as I will comment on at the very end, I think that it would be really interesting actually to make these two different paradigms of machine learning coexist somehow and exchange information with one another. So the idea, as I sort of already anticipated, is that we build surrogate models for quantum mechanics. We have actually pretty accurate first principle methods if you can afford the computational cost. And the idea is that after having done a few of these calculations, rather than keep computing roughly the same energy over and over again, we build a surrogate model that after training is capable of predicting not only the interatomic potential, that arguably is one of the most important properties because it drives structure and stability, but also all sorts of functional properties. So we have been working in this space along different directions, and one that I want to mention because I think it informs a lot of what we have been doing is an effort to try and rationalize what machine learning models compute. And the idea is really that very often machine learning is used a little bit as a package. I mean, when you use ChatGPT, you are really using the training set, the structure of the model, all the people who have tried to align it so that it doesn't suggest you how to kill your mother, and that's the product that you get. And I mean, it works pretty well. So what we have been trying to do, however, is more to sort of deconstruct the different machine learning models that have been very successfully applied to this class of problems, with the idea in the end to provide some kind of modular framework that people can use to put together the pieces in the way that makes most sense for the data richness regime, the type of application, how extrapolative you need to be, and so on and so forth. So when you try to do this process of deconstruction, and you get down to the very basics, all of the atomic scale models that try to map crystal structures or molecular structures through the properties of a specific configuration, as you could compute from quantum mechanics, use as ingredients the positions and the nature of the atoms. So essentially, we're working with either point clouds or alternatively, but equivalently, with a graph representation in which, however, we decorate the edges of the graph with information on the geometric structure of a molecule or a material. And so, on top of these very basic mathematical structures that are also used in a bazillion different fields, from autonomous driving to facial recognition, and you name it, we have additional constraints or priors, depending on how you want to see it, that are basically fundamental laws of nature, such as invariance to symmetries, or well-founded expectations on how matter behaves at atomic scale. So, for example, that the properties that you compute from an electronic structure calculation would usually vary smoothly as you deform a molecule, and that generally, at least for a large class of interactions, there is an additive property that allows you to decompose the properties of a large system into contributions that come from relatively short-ranged local terms. So if you look, and then you could do a similar figure for many other fields, the speed at which the field moves is so insane that there is really an explosion of alternative frameworks, alternative models, and we have been focusing in particular on the problem of how you represent a structure. So in a certain sense, the first step after you take a molecule, you start from the Cartesian coordinates that don't fulfill all of these symmetries, and you try to map these into descriptors, in geometric descriptors that are symmetric, smooth, and local or additive. And actually, when you look at this wealth of different frameworks, it's sort of interesting to see that by and large, you can regard all of these as variations on the same theme. And this same theme is basically describing a structure in terms of correlations of the neighbor density. This is pretty much the same. I mean, mathematically, ends up being exactly, I would say, the same framework that goes behind ACE, and is also very, very closely connected with what Alex Shapib has been doing with moment tensor potentials. But essentially, you are regarding a structure as a correlation of the neighbor density symmetrized over rotations, so that basically your descriptors become invariant invariant, I would say, to rigid rotations, which is one of the symmetries that you want to enforce. Now, it's actually quite easy to imagine what these correlations would look like if you take just one density, you integrate over all the possible rotations, the only information that remains, information on the pair distances between atoms. So this is basically describing a structure as the pair correlation function, and if you build a linear model of this, you get a pair potential. If you get a nonlinear model, you get something more, but you still have a limited amount of information. This is why it makes sense to compute tensor products that incorporate additional information so that you have a description that is richer to the point where, as Ralph has almost certainly shown you, you can build linear models that are extremely accurate and efficient just because you end up having a complete basis to expand any symmetric interaction. Now, what I like about this formalism is that it's very extendable, and it allows you to show that you can do more with this. You can basically incorporate a set of spherical harmonics inside the symmetrization integral, and this gives you essentially a reference system, a basis on which you can expand the properties that are not invariant but are equivariant, and I will return on this later. You can also extend these to describe models in which you pool information on the environment of neighboring atoms, and so now the correlation is not between the densities centered on a single atom, but between the density centered on atom, the density centered on the neighbors, and information that tells you what is the relative position of the neighbor to the central atom. And I hope you can see from this drawing that this is really the structure of a message passing network, because you have information on the neighbors, information on the relative position of the center of your environment with the neighbors, and then you sum over the neighbors, and basically this is equivalent to pooling information from the neighbors in a message passing architecture. Now, doing all of this was a lot of fun, but I want also to tell you a little bit what kind of developments you can squeeze out of this understanding of these descriptors in terms of density correlations. And I want to give you a recent example. Actually, the idea is a few years old, but we applied it in full only very recently. And actually, the idea comes from realizing that if you just apply this idea of density correlations naively, the complexity and computational cost scale very poorly with the number of atomic species that you have, because since you want to distinguish whether your neighbors are boron, nitrogen, or carbon, when you build your correlations, the dimensionality of the correlation space grows exponentially with correlation order, and the basis of this exponential is the number of species that you have in your system, because you want to describe pair correlations between nitrogen and boron, nitrogen and carbon, carbon and carbon. With 3 centers, you need to describe correlations between 3 types of atoms. And if you have the whole periodic table, this spirals out of control very, very quickly. So the idea that we had actually back in 2018 was to essentially do a tensor contraction for this density, projecting. So the idea actually, metaphorically, but also quite literally, I mean, it's quite an accurate metaphor here. The idea is that rather than describing a system in terms of well-separated chemical elements, we describe the elements as linear combinations of alchemical pseudo-elements. Okay, so here I'm using, I'm kind of joking on using earth, fire, and water, but actually it's quite a fitting metaphor. So each atom becomes a linear combination of different archetypal element types, and then your machine learning model learns simultaneously the behavior of these archetypes, so how the correlations between the archetypes translate into a property, and simultaneously the composition of the elements into this property. So less metaphorically, what we are doing is a contraction of the, I don't know, 20, 80 elements that you want to work with onto 3 or 4 dimensions, and then build correlations only in this contracted space. So as I mentioned, we applied this quite recently, and we applied this to a specific problem, which is the description of high entropy alloys based on transition metals. And actually, kind of fortunately, the PhD student who was working on this, Natasha Lopanitsina, decided to select not the whole D block, but only the elements that are used often or reasonably often in making high entropy alloys. So we ignored, technetium for obvious reasons, cadmium and mercurium because they are very toxic, and also rhenium and osmium because, matter of fact, they are never used. And then basically, we tried to build a machine learning potential that can deal simultaneously with all 25 elements. If you try to do this brute force, by the time you are at correlation order 3, you have 25 to the third element, so you really cannot handle this. And so we tried to build models built with this structure of a contraction followed by the calculation of correlations in the pseudo-element basis. And we try to do this using different sizes of the pseudo-elements. And so we start, for example, with 2 pseudo-elements, and you see, the error is not great. The model kind of saturates at an accuracy of about 80 millielectron volt per atom, which is really not good. And you can understand this because clearly a 2-dimensional space is not enough to describe the diversity in chemical behavior across the metal block. But then you go to 3 pseudo-elements, and you see that the saturation is still there, but it goes down by a lot. And then if you go to 4 or 5, the improvement is actually pretty limited. And I should stress that here we are limiting the correlation order to 3 body descriptors. So basically what this is telling us is that if you're limited to 3 body descriptors, your problem at this point is not anymore the chemical diversity, but is the restriction on the correlation orders that you consider. And basically, since we wanted really to focus on this chemical diversity more than on the model, we just went back to a old school Beller-Parinello style neural network on top of these contracted descriptors. And you see that these, even keeping the pseudo-elements to 4, allows us to further improve the accuracy of the model and basically get below 10 MeV per atom, which is definitely not accurate enough to capture the subtleties of the behavior of binary alloys, but it's semi-quantitative for a potential that handles 25 elements is not bad at all. Now, more importantly, at least equally importantly, in my opinion, the fact that we use this relatively simple contraction scheme means that we can interpret quite easily what the model is doing, because remember, if we project the elements to a 3-dimensional element pseudospace, each element, chromium, manganese, or whatever, is a vector in 3 dimensions that describes the composition of chromium, manganese, iron on the basis of these 3 pseudo-elements. So we can visualize the weights in this form, and I find it really, so basically this shape, this sort of U fold of the periodic table comes out from the optimization of the potential. So basically the optimal weights, the weights that allow to describe as well as possible the behavior of these elements using a three-dimensional pseudo-element basis, is very, very much reminding us of the shape of the periodic table. And also, I should add, a couple of years ago was the International Year of the Periodic Table, so there are a number of different alternative periodic tables that you can find, and there is this form, which is like a spiral, and I find it interesting that the transition metal sector here is also folded into this U shape, and actually, in many respects, the zinc and scandium are closer to each other in behavior than scandium and manganese. So it does make chemical sense. And so something that we did, which I also find quite interesting, is the fact that since we had left out rhenium and osmium, sort of serendipitously, we could try to put them back in just by interpolating their weights between tungsten and iridium. And it turns out that the potential that basically does no training at all on rhenium and osmium containing structures, of course, it doesn't do as well as a potential that is trained on rhenium and osmium, but it works well enough that you can run molecular dynamics with it. And I think that this is very interesting because in a certain sense reinforces the notion that there is something in these projection weights. And I also like it because it's a reminder that when we talk about interpolation or extrapolation is always relative to the feature space that we're using. So with this alchemical compression, making a prediction for an element that is nowhere in the training set is actually an interpolative exercise in a certain sense. So just to give you an example of what you can do with this, I don't know how much, this is a very diverse audience, but high entropy alloys were originally discovered because actually two groups independently, Ye and Cantor's group, discovered that when you quench a mixture of in equimolar parts of just a kitchen sink combination of 20 or so elements, you get fewer distinct phases in the microstructure of the quenched material than you would expect from the phase rule. And so basically we sort of repeated this experiment on a computer by simulating 25 elements simultaneously. And then, this is basically, it's actually a pretty sophisticated sampling simulation in itself, because we combine molecular dynamics, replica exchange, and Monte Carlo swaps of different elements. And at the end, we can sample the propensity of different elements of staying together, which in a way could be a guidance to the design of new high entropy alloys. And I don't know, I think that this is an interesting example of how trying to understand better the structure of a representation allows you also to design new methods and build useful potentials that can handle a large sector of the periodic table. Now, in a way, more something which in a way is simpler and has been around for quite longer, at least I would say at least 10 years, is actually just using machine learning to make ab initio thermodynamics cheap. And this is something that we have been doing for a while. So we have done these, for example, for the relative stability of the different phases of water. And I like to show these results because they are, they're actually, again, they are pretty sophisticated. So in order to study water, you also need to describe the quantum nature of the hydrogen atoms, which requires complicated and very expensive calculations. So this is kind of simulation that would be completely impossible without decent machine learning potentials. You can study matter in extreme conditions, and I will return actually on these later on. And you can also build phase diagrams of materials with first principles accuracy. And actually, so here I'm showing you the binary phase diagram of gallium and arsenic. And something that sort of jumps to the eye here is that the accuracy in comparison with experiments is not so great. So the melting point of gallium arsenide should be around 1500 Kelvin, and instead we predict around 1200. So this actually points to the fact that machine learning makes many new things possible, but doesn't solve all problems. And some of these are intrinsic of machine learning, but others are actually problems of the reference DFT calculations that we do. And in a way, it's interesting to be able to tell whether this error is due to the machine learning model or is due to the DFT reference. And actually, this is one kind of simulation in which trying to repeat the simulations explicitly with DFT, I don't know, perhaps it would even be feasible, but we would burn, more, we would generate more CO2 than it was used to train GPT-4. So it's probably not a good idea to do that. And so here I want to tell you just 5 minutes about uncertainty quantification, which I think is something which is getting a little bit more attention, and I think it's really important, because when you put machine learning into the mixture and you have experimental uncertainties as well, I think it's very important not to add uncontrolled sources of error on top of the sources of error that you already have. And what is nice about machine learning is that since it's essentially a statistical technique, it's very easy to build pretty well principled estimates of the uncertainty of a machine learning prediction. Now, what we use here, it's an ensemble model. We are using kernel models, which actually makes it pretty cheap to do these ensemble and committee models. The same would be true for linear models. But the reason why we focus on a committee of models, so basically we make predictions using models that are trained on different subsamples of the overall training set. And then when we make a prediction, we can compute not only the mean of the predictions, but also the standard deviation, and that's our uncertainty estimate. Now, it turns out that much like the uncertainty that you get from Gaussian process regression, usually this is a very good qualitative estimate of whether you're accurate or not, but it's not very quantitative. And so what we do to make this estimate more quantitative is very simple. We basically rescale the uncertainty with a log likelihood maximization idea. And something which is very important is that we don't just rescale the uncertainty, but we actually recalibrate the spread of the committee around the mean. So basically, we apply a rescaling that leaves the mean unchanged, but rescale the variance in the correct way. And the reason why this is important is that it makes it super easy to do uncertainty propagation, because basically, if we want to use the prediction of the machine learning model for something, we can just apply that procedure to each individual prediction. And by doing this, we get a propagation of the uncertainty of the machine learning predictions onto the final property. And this is particularly useful if you want to compute the uncertainty that comes from sampling. So if you do molecular dynamics, you observe different configurations of your system, and then you compute an average. But if you use a different potential for sampling, you will explore different configurations, and so the averages that you compute will be different. Now, how does the uncertainty on your potential, the 8 MeV per atom that we were having for the high entropy alloys, how does this propagate on the thermodynamic average that you compute? How does it translate on the melting point of gallium arsenide? And so the idea that we had is basically to use a old technique, which is theoretical law, I think back in the 70s, which is to reweight the basically, we just run a single simulation and we compute statistical weights that allow you to compute averages relative to a different potential. So we just run a simulation with the mean potential, which is our best estimate, but we can reweight the averages to get the prediction that we would have had with potential number 1, potential number 2, or potential number 3. Now, these estimator is actually statistically unstable, so we use a cumulant expansion. This is a small but important detail, because most of the time this kind of reweighting fails dramatically because there is very little overlap between the configurations that we have sampled and the configurations that are compatible with the other potential. But basically, what we can do with this is take a simulation of the coexistence between gallium arsenide and molten gallium. We do an interface spinning simulation, which is a simulation in which we keep the relative fraction of the liquid and the solid constant, and then the force that acts on this constraint tells you on how much imbalance is there between the chemical potential of the liquid and that of the solid. And then basically you do this at different temperature and you find the point where the chemical potential difference is 0, and that is the melting point. And so this is, again, a pretty complicated simulation, and we are doing this, and here I start sort of emphasizing that combining advanced statistical sampling with machine learning is not trivial, and we do this by having a very modular design. We use this IPAM code, which is a Python software that does molecular dynamics and has pretty advanced sampling techniques implemented and communicates with external codes using a socket. And this is nice because this is very loose coupling. You don't have to define a common API. You don't have to compile together. This is very, very convenient. And so here we use Plumed, with this, which is a free energy sampling code to compute the pinning potential. And we use LAMPS, which is itself compiled with a neural network code to get the ensemble of predictions. So at the end of the day, when we compute our phase diagram, we actually have an ensemble of predictions. So we can reweight the difference in chemical potential to get the one that corresponds to each of the members of the committee. And in this way, we don't get just one point where the chemical potential is 0, but we get the point where the chemical potential is 0 for potential 1, 2, 3, and 4. And we can do this for the different compositions, so pure gallium, pure arsenic, and gallium arsenide. And the uncertainty is different for each of these. And this would be very hard to tell based on the accuracy of the raw potential how these would translate into a complicated property such as the melting point. But with this technique, we can do this estimate basically at no additional cost. And this means that we can put error bars on this phase diagram and tell quite conclusively that the discrepancy that we observe for gallium arsenide is not the fault of the machine learning model, but is the fault of the reference DFT calculation. And so, if we wanted to make this prediction better, we probably shouldn't improve the machine learning model, but we should use a more accurate DFT reference. Now, this far, I've gone beyond potentials in the sense that I've been doing, I would say, fairly sophisticated sampling techniques on top of the machine learning potential. But another direction in which I think it's really necessary to go beyond the prediction of potentials is to be able to predict the functional properties of materials. Because if you want to build a device, knowing that a certain material is stable is not enough. You also want to know how it will perform as a ferroelectric, as a semiconductor, as a topological insulator, you name it. So one of the challenges then is that a lot of these functional properties, take for example the polarization in a ferroelectric, are not scalars. So they are not invariant as the potential, but they are covariant. So if, for example, if I take the dipole moment of a water molecule, I want that the prediction for a rotated molecule is exactly the same prediction, but rotated by the same rotation that I have applied to the geometry. So the idea here then is that we need a model that is equivariant, and we have been doing this for quite some time, and one way of doing this is by defining descriptors that basically carry a symmetry index. So for example, if I want to learn a dipole moment that is a vector, I need descriptors that don't only have features that describe atomic environments, but also have an additional index that tells me whether I'm trying to predict the X, Y, or Z direction. So basically, you can show that for a descriptor to guarantee equivariance, the descriptor itself has to behave like a vector. And more in general, if you want to learn something which is not just a vector, but is a tensor, you need a family of descriptors that transform like spherical harmonics, because spherical harmonics provide a complete basis to expand any equivariant property. So basically, you need a family of descriptors with these properties. Now, once you have this family of descriptors, there is a lot that you can do. You can predict dipoles, polarizabilities, but you can also predict properties from quantum calculations, such as the charge density. The charge density, you can describe it as a combination of atom-centered terms, and if you expand each of the atom-centered terms on a basis of spherical harmonics, you have a bunch of coefficients that transform like spherical harmonics, and so you can predict them using coefficients that essentially behave like spherical harmonics under rotation. You can also predict the matrix elements of a single particle Hamiltonian. You could see this basically as a glorified tight binding. And what is really nice is that by making your model equivariant with respect to atom permutations and rotations, you automatically build in all of the point group symmetries. So you don't have to tell your model that benzene has a six-fold symmetry. Your model knows, which means that some of the qualitative features of the physics of benzene, such as, for example, the degeneracy of some of the energy levels, is exactly built in. And you don't have to do anything to learn it because it's built into the symmetry. So a few examples of applications that can do with this. We built a model for barium titanate that doesn't only predict this. So this is a ferroelectric. It's a material that develops a spontaneous polarization, and it's kind of a fun material to work with because it undergoes many phase transitions from a rhombohedral to an orthorhombic to a tetragonal to a cubic phase, each with a different orientation of the macroscopic polarization until in the cubic phase, your material becomes paraelectric. And what is nice is that not only we can describe the thermodynamics of the phase transitions, which is what you would use a potential for, but we can also compute functional properties such as the temperature-dependent dielectric constant of this material, which in the end, since it's a ferroelectric, this is the type of properties that are important to design a device. So you can also incorporate some electronic degrees of freedom. For example, here, this is the heat capacity of nickel, and we can do advanced sampling, so we can capture the quantum mechanical behavior of the nuclei at low temperature, but we can also describe explicitly with a machine learning model the density of electronic energy levels, so that we can also describe the electronic excitations that occur when you are at high temperature. Nickel is often used in high temperature applications. So basically, it's I mean, I don't know if it's really important, but it's at least desirable to incorporate also the electronic excitations in the description. Yeah, you can. I mean, this is a little bit of a overview of what you can do. You can compute spectroscopic properties of liquids. This is IR and Raman spectra of liquid water. And what is nice here is that actually these, I used to do this as a postdoc, actually, first principle calculations of quantum dynamics in aqueous systems. And I don't want to tell you how much, how many CPU hours I've burned to run these type of calculations. These are really, really expensive calculations. And now with machine learning models that give you potential, dipole, and polarizability, these are really something that you can do almost routinely. So I sort of anticipated when I started that I wanted to tell you a little bit how I see the place of machine learning in all of these. And one of the things that I'm really convinced of is that it doesn't necessarily make sense to throw away 100% all of the physics-based modeling. Just to give you a concrete example, so if you predict the Hamiltonian, usually you do this in a localized basis, and if you predict the Hamiltonian in a localized basis, in order to do something with it, you also need the matrix that tells you how the orbitals on different atoms overlap. Now, you could machine learn this overlap matrix, but it's kind of silly because actually for most bases used in quantum chemistry, computing the matrix elements of the overlap matrix is incredibly cheap. So this is a case in which there is a problem that is difficult, learning the Hamiltonian, and another which is super simple. So I basically see no point in machine learning the overlap matrix because it's so cheap to compute. And another example of what you can do with this is the description of matter in really extreme conditions, like what happens when you heat up the matter at 50,000 Kelvin. Now, the idea that you can describe matter at 50,000 Kelvin in terms of the ground state energy, so basically the energy when the electrons are in the most stable possible configuration, doesn't make too much sense. And what you need to do is to describe the free energy of the electrons that involves the ground state energy, but also electronic excitations and electronic entropy. And what is nice about what we try to do here is that we don't try to predict these electronic free energy directly, but instead we learn the ground state energy and the ground state electron density, sorry, the density of states. And these are basically all the ingredients that you need to be able to predict the electron free energy at almost arbitrary temperatures. And so, here you see how I'm combining machine learning predictions for two quantities that are hard to compute with an expression that is physics-based, and it's a one-dimensional integral. So this is really cheap, really easy to do, and I don't see any point to eliminate these physics from the modeling. Now, more generally, I think that I think we are a little bit lagging behind. There are many people who are already doing this, but this is something that I would really like to do, is incorporating more or less directly experimental data in simulations. And I think that this is an interesting problem because from a conceptual level, what experiments compute is different from what theory computes. There is pretty much no experiment, even if you do, imaging with a free electron laser, you don't really capture the properties of an individual configuration of the atoms. You're always averaging over an ensemble of configuration, which makes actually this mixing of theory and experiments not entirely trivial. So I think that this is an interesting problem to work on. And another problem, which I think is going to be more and more important as this combination of machine learning and sampling makes it possible to simulate more systems or more complicated systems, is also how you interpret the outcome of simulations. And this is also something which we're trying to work. This is a paper that was really spearheaded by a former postdoc of mine, Rose Sersonsky, and we study what makes a molecular crystal stable. So here we're not trying to be very accurate. It's very hard to get the level of accuracy that you need to predict the stability of molecular materials, but we're trying to get a qualitative understanding of what types of interactions can stabilize a crystal, which I think is very important in designing new materials. Very often, you have so many other constraints that having a intuitive understanding of what are the properties that you're looking for is something that can be very, very valuable. And so we do this. I really don't have time to get into details, but I invite you perhaps to go and read the paper and look at this website. We basically do this by building maps of the different motifs that you find in a molecular crystal, classified based on how much they contribute to the cohesive energy of the crystals that are part of a reference training set. So another point, which I think is a very important side effect of looking at the nature of the representations that we use, is what I like to call model introspection. So basically doing ablation studies to understand what interactions are important in your system. For example, given that we use local models, you can try to artificially restrict the information that you feed to your model to a fixed cutoff distance. And by doing that, you can understand how much, basically you can look at how accurate are your models built based on artificially restricted information, and this tells you how much interactions at different ranges contribute to the property of your material. So in a way, it's a way to test the hypothesis on whether I don't know, long-range interactions important for my material? Well, you can tell by artificially restricting your machine learning model not to include any interaction beyond a certain cutoff. And then if it cannot learn a property, it means that those correlations are important. And in this direction, I really think it would be very useful to try and combine end-to-end predictions with the more systematic and analytical investigation of the mechanisms that underlie the behavior of a molecule. I think there is a lot of potential in here. So the picture that I have in mind and is really one in which you use machine learning as some kind of information glue, and you use it to combine information from, the level at which I'm using this here is really more to combine machine learning and physics-based models and try to make machine learning more interpretable. But many of you and many of the talks that I could follow are showing very clearly how machine learning also has an impact on laboratory automation, on data mining. And I think that we should really work as a community to bring all of these together and make different software tools interoperable with each other. So in my little world, at least this is something that we are really trying hard to do. We're trying to build tools that are modular and interoperable, and lately I've also been trying to sort of atomize the problem and building small libraries that do one thing and they do it well, like sort of the GNU philosophy, and so I hope that this is something that will be useful for the community and not also for us. So with this, I want to wrap up. I want to show you the faces of the people who did most of the work. I also want to give you a couple of references in case you are interested. So these are a review that we wrote a couple of years ago on representations that is not yet completely outdated, despite how quickly the field moves. And some of the ideas about combining machine learning with physics-based modeling, I tried to talk about in this perspective. So thank you, and I hope you have a few questions, and I will be happy to answer.